All right, so we have an exam week from today. It's not comprehensive, so I won't be asking questions about adding binary numbers and converting to hex. However, you are going to remember some things like truth tables and K-maps, and we'll see why you need K-maps today, actually, because today is kind of a really fun topic for me to start talking about, because it's really the last tool that you need to understand to be able to design a complete system, which is how do we design a control system? How do we design the circuits that decide what we do based on the inputs with memory, right? Because we can design like the launch controller that just takes the inputs and asserts and outputs based on what they are. But how do we design something like the calculator that we're planning to build for our final project we're building up, which is sending out control signals? Or how do we design, say, a traffic light, right? Which we know if I pull up to a traffic light and it's red, it's waiting on some timer to finish counting down before it goes to green, right? And the tool that we're going to learn for this is called state machines, or specifically finite state machines, FSMs. Or generally, I'm just going to reference state machines. Finite state machines just means there's some limited number of states that can exist. One way to think about state machines, like an example of state machines, are literally every board or card game is a state machine. So let's take the simple one. Let's take tic-tac-toe. This is a state. We would call this empty state, right? We would start up. So if we were thinking about this in terms of, like, if I wanted to build a video game on my FPGA that was this, we would start out in some state that is empty. I'm just going to call it empty. And it turns out this is just an art class, right? Because everything we do is just drawing something. So we've drawn block diagrams, timing diagrams, and on and on and on. We're just drawing diagrams. Well, this is going to be, I'm just going to start out with just a rough idea, and then we'll formalize how we do it. But this is a state machine diagram, or SM diagram. And this is how we talk about a control system for digital logic, mostly. But if we start empty, this would happen when we reset, right? We push the reset button, we're going to come in and we're going to have an empty tic-tac-toe. Now, as soon as that does, we're going to enter a new state. And that new state is going to be, we're just going to call it wait X. And it's going to wait on where does X want to go. And now there's a couple ways that I could represent this next part, and I'm going to do it kind of the bad way. There's 9 squares, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And this waiting on X is just going to sit there as the clock runs, just waiting for someone to push one of those buttons. And then it might have another state called draw X, where it's going to move on and it's going to draw the X, right? Because if it's a graphic, it needs to put the X somewhere, and it's going to take the input that you put and it's going to draw it on the X, and then it's going to go to a new state, which is wait O, right? Because now it's the O's turn, pick the X, and then it's going to wait on the input, draw O, and then go back to wait X. Right, that's the game. Now, obviously, this is not a complete state machine because this doesn't have like the check for win conditions and that kind of thing. So I could add like an extra state or wait for the inputs, draw the X, check for win. If not win, wait O. So this is conceptually all a state machine is what is the current situation of whatever I'm designing? Where are we right now? Your phone is essentially a state machine, right? Where it's on its idle screen, and in my case, it unlocks with fingerprint, so its state is wait on fingerprint, right? That's what it's doing, is it's just looking for some input to tell it where to go next. So in order to formalize this, I'm actually going to simplify it down to one of the easiest state machines that we can design. And this is going to be very close to whatever ends up on the exam when I talk about it. So there will be a homework posted today. I'm going to do it after class. It'll be up before 5 o'clock. That will go through practice just what we're doing here. And then we'll learn more about how to implement it in like Vhdl and more sophisticated state machines. But the simplest state machine that we can really talk about easily in a full design sense is what's called a sequence detector. And all a detector means is it outputs a 1, right? It says true if it detects whatever it's interested in. So like an oxygen detector would try and detect oxygen. If there's oxygen, it would output some voltage that says, hey, there's oxygen here, right? Well, in this case, a sequence detector is going to look at a sequence of numbers and then assert true if we see that sequence. Okay, so let's say we're looking to detect 0, 1, 0. So I'm going to have some long string of numbers that's coming through one at a time, and I'm looking to send out a signal that says I just saw 0, 1, 0 for whatever reason I'm interested in that sequence. So just like the tic-tac-toe example, we're going to come in from some reset, right, into some state, and I'm just going to call it state 0. Okay, and now its whole job is wait and see if I find a 0. But if I don't find a 0, I stay put. So this is the formal way of doing a state machine, which is I'm going to label my inputs on the arrows. So this is an input. My input was a 1. I don't advance state because I'm looking for a 0. The next state, state 1, is basically saying I've seen a 0. Now I'm ready to start looking for the 1. Well, if I see a 0, which is not what I'm looking for next, we're going to stay in the same spot. Because that state is I've seen a 0, right? That is, I just saw a 0, so I'm here. So this is, I saw a 1 in state 1, stays put. I saw a 0 in state 0, goes to state 1. If I see a 0, I stay put. If I see the 1 I'm looking for, I move on. Right, that's the 1. And now here, I need 2 different options, right? It can either be 0 or 1. It's 1 input, 1 bit. If it sees a 0, then it has succeeded, right? I've now detected my sequence because I saw a 0, 1, 0. Now the question is, where do I go? Well, it's going to go back to the I just saw a 0 spot, right? Because it just saw a 0. If it sees a 1, then that means I've gotten the sequence 0, 1, 0, 1, which you'll notice here is where I did the detection, but I'm about to be ready to detect another 0, 1, 0, potentially. The 1 puts me back to here because if it's 0, 1, 0, 1, 1, I go back to, well, 0, 1, 0, I have the detect, then I saw a 1, well, then the next one, the 1, 1, isn't anywhere in the sequence. We'll go all the way around. There's 1. It started over, right? It's not there anymore. We need to start looking for the next 0 before we can start progressing through the states. Now, to make this completely formal, the complete version is I brought these as inputs / outputs. So here, 0 / 0, right? Because I'm not outputting. I haven't detected. I still haven't detected it. I didn't detect anything. I did. So input was 1, output is 1. So this is saying is I'm in state 2, I see a 1, that, oh, sorry, I reversed that. Sorry. I'm in state 2, I saw a 0, that means I've detected my sequence. Now, this is going to step through as each each of these questions, right? Is it a 0? Is it a 1? Is going to be associated with the rising edge of a clock or falling edge of a clock because it has memory. I have to decide where am I and where do I go? But to remember where I am, that means there's a flip-flop of some kind, probably a D flip-flop. And so we go, okay, I'm at state 0. There's a rising edge of a clock. Let's look at the input and see where I go from there. So to build this, there's really 3 components to it. There's what we're going to call the current state register, which is just D flip-flops. How many D flip-flops do you think we need to build the current state register for that state machine? 2. Because there's 3 different options, which I can represent with 2 bits.
Oh, okay, yeah.
Right? So keep track of that, right? We don't need it 1 bit for every one. We need just enough bits to cover all possible scenarios. So that means I'm going to have 2-bit registers. Now this signal that's coming in, so I'm storing the current state. So that makes the output the current state signal. That is where I am. The input then is going to be my next state signal, which is where am I going the next time there's a rising edge. So now I need some block of logic that tells it where does it go. Well, what do we consider when we decide where we go? It's the input and the 2 bits of the current state. It's where I am and what are my inputs, which decides my next state. So there's some block of logic that we're going to call NSD for our next state decoder, right? The decoder is something that takes information in and asserts an output that is translated to the form that you need. In this case, the thing that is decoding is where are we, what is an input, and the output of the decoder is where are we going, this next state signal. So its inputs then are current state and I for in. Okay, then the only thing that's missing is what is my output? And what does my output care about? Well, my output cares about where am I? What is my current state? And what is my input? Making this our output decoder. And this I'm going to call Z for out. I'm not going to do O for out because my O's look like zeros and that gets confusing. This is every state machine ever. Almost. We're going to have one other form of this that we'll talk about in this class, but this is an easy version. This one is called a Neely state machine. Now, we're going to go ahead and we're going to represent this a few different ways. In order to facilitate like the idea in time is how does this change in time? Let's do a timing diagram, right? That's the easiest way. So it's a clocked system. And we're going to need to look at basically what is our current state, what is our next state, and what are our inputs, right? So let's go ahead and put our input here, I for input, and I'm going to start out saying it's a 1, 0, 1, 0. So here I'm going to have a 0, 1, 0. And then I'm going to have 0, 1, 0, 1. 1, 1. Let's do 1, 1. There we go. Okay. So that means that each rising edge of the clock, it's evaluating what is my input. Now, if we treat the next state decoder that looks at where am I now and what is my input as ideal, that means there's no delay, then let's go ahead and start evaluating what is my state. Well, the way this is going to work is essentially we're always going to start in state 0. And at this moment in time, the clock hits, the current state is going to look at what is my output of the next state decoder. Well, my next state is I'm in state 0 and I saw a 1, so I stay in state 0. Right, that's what the diagram tells me. Now I see a 0, that tells me move to state 1. Now I see a 1, move to state 2. Now I see the last 0, move to state 3. See a 1. Sorry, not state 3. Sorry, I sometimes I do the 0. Last night I did this not 0 index. So anyway, so we've gone state 0, saw 1, don't go anywhere. We're still in state 0, saw 0, go to state 1, 0, 1, 0. If I'm in state 2 and I see a 0, I go back to state 1. Right, that's what this is telling me. Go back to state 1.
So you go back to state 1 and also other signal come out saying.
Yeah, but we'll do the other signal on the another row. So let's just right now worry about just where do we go. So now we're in state 1 because we were in 2 and we clocked in a 0. We went to 1, we're in 1 and we saw a 1, and it looks like I may have messed this up. So 0, 0, 1. So I've seen
Now you go to state 2.
0,
Stay in state
1, 0. So state 2. And then if I see another one, why did I do that? State 2, because I need that. So I clock in the state 2. When I see a 1, I go to state 0. And now I clock in a 1, and I've seen another 1. State 0. Now my Z output, as you just mentioned, is basically just going to be 0 because the only time, well, it's going to start out 0 because I'm in state 0. And the only time that it might be anything other than 0 is these times when I'm in state 2. Okay, so I'm just going to fill in the zeros because if I'm not in state 2, sorry, some of these got a little off center. There we go. If I'm not in state 2, I can't possibly be 1, right? State 2. So now the question is, am I in state 2 and I see a 0? Well, that happens here. And it happens not here.
So your Z is not clocked.
Your Z in this situation is not clocked because it's just logic that is basically saying, and we'll do it, we'll design this actually, this output decoder, but it's just saying if I'm in state 2 and I see a 0, then I have detected it. That's my output. Okay. So that's what's happening in time for this type of Neely state machine. We'll get to the modes that actually behave differently. Yeah.
Why does it drop on the rising edge if it's not based on the clock?
Because, so here?
Yeah.
Because the clock changes from state 2 to state 1. So we basically have an AND gate.
state one. Okay.
that this is 2 bits that is right, because this is my 2-bit state. So this is saying I want state 2 and I is
Okay.
1. So as soon as this changes, which happens on the rising edge of the clock, that stops being true. That's why. So I'll give you a peek ahead just a little bit. So the other type of state machine we'll talk about is a Moore state machine. And the difference is it doesn't care about what our inputs are. Its output is strictly based on the current state. So its behavior would do what you are all thinking it should do, which is be true for the whole state too. Unfortunately, that's where the Moore state machine is helpful, but it adds a little bit of complexity. And the mnemonic to remember the difference between Neely and Moore is Moore takes more states to design. Its state diagram is more complicated in exchange for simpler logic at the output decoder. It's kind of a trade-off that we'll get to on why in just a minute. But let's go ahead and figure out, are we okay if I erase this timing diagram? Okay. So I want to leave up the other material for a moment. So let's introduce another way to describe these that actually turns out to be a little bit better to help us design these circuits. And that's going to be the SM table, the state machine table. So the state machine diagram is that. The state machine hardware is this. And the state machine table looks like this. Which the first thing we want to know is our current state. Where are we? And that has 2 aspects to it. The first is the name we give the state. And the other aspect is the code that is associated with that state. What's the binary representation? Okay. Then the next thing we need to know is our next state. Where are we going? But our next state has a dependency, right? Our next state cares about 2 things, which is both where are we and what is our input. And the last thing we need to know is what is our output, and it also cares about what is our input. Now we're just answering the question. And if we drew the picture right, it turns out the state machine table is really easy, because now I just say, well, if I'm in state 0 and I see a 0, then I go to state 1. If I'm in state 0 and I say a 1, I stay in state 0. If I'm in state 1 and I see a 0, I stay in state 1. If I see a 1, I go to state 2. If I'm in state 2 and I see a 1, a 0, I go back to state 1. But if I'm in state 2 and I see a 1, then I go all the way back to state 0. But there's 2 bits. I have leftover state. This is, I don't care. I'm not supposed to be there. Let's not do that. Our output is easy, right? The only time that we're going to assert our output is if I'm in state 2 and I saw a 0. So state 2 saw 0 is this one. That makes 0, 0, 0, 0, 0, don't care, don't care. We get to use the don't cares here because, again, we shouldn't be in state 4 in this case. Or, well, state 3, the 4th state. I should never use that. So I get don't care, which will simplify our K-maps. Well, let's build a K-map out of this, right? That's the next step, is because that's what we want to do, is I want to build this next state decoder circuit. Now that next state decoder has a 2-bit output. Do we know how to do a K-map that outputs 2 bits? No, right? It's 1 bit per output when we design a K-map. That means we're going to need 2 K-maps. So our first K-map is going to be specifically for how do we determine the smallest bit of our next state. And it's going to depend upon input CS0, CS1. Right? 2-bit input, sorry, 2-bit current state, 1-bit input. That's where I'm getting this map from. 1, 0, 0, 0, 1, 1, 1, 1, 0. Right? Remember to flip the 2 to maintain logic adjacency. Now, it's a little bit beneficial, especially now that we go and just start labeling what these are. So state 1 is 0, 1. State 0 is 0, 0. State 2 is 1, 0. State 0 is 0, 0. Because now what I get to say is that this column and that column are NS0. That's the smallest bit of my next state. Similarly, that column and this column are NS1, right? Our next state has 2 bits. That's what those are assigning is, let's decode our inputs, which are current state and I, to generate these outputs. Okay, that literally just means we come into our K-map and say, well, when I is 0 and my state is 0, 0, that's this square, and that means my next state should be 1. That's this 1 right there. Now, if my I is 1, I get a 0. If we're in state 1, so 0, 1, which is this column, and I see a 0, I get a 1. Next is a 0. We skip a column, we come over here, we get the 1, then a 0, and don't care, don't care. I fill up my K-map by circling that. I now say NS0 is, well, the only thing that doesn't change is I. So NS0 is equal to not I, right? Because I doesn't change and it's a 0. Remembering our K-maps from forever ago. There we go. That's the 0 bit of my next state. If I want NS1, we're going to have the same mapping, I, CS0, CS1. And now that we've done the order once, it turns out it's really easy to finish this next K-map because I just go 0, 0, 0, 1, 0, 0, don't care, don't care. That leaves me with this one. And I get to say NS1 is equal to, well, I doesn't change and it's 1. So we have I, and in the middle, CS0 doesn't change, right? And it's 1, so I and CS0. So now, if I were to draw this next state decoder block, that means I have inputs CS0, input CS1, input I. Then I have outputs NS0 and NS1. Sorry, let me draw that NS1. Those are my two outputs. These two combine into that 2-bit vector that we call next state. And now it's just a matter of saying, well, NS0 is not I. So I'm gonna take this, bounce up here, throw an inverter on it. Done. NS0 is taken care of. NS1 is I and CS0, so it needs an AND gate. It's going to take I and CS0. Done. That. Don't even need CS1. It simplifies out. Okay. Next, we need to build the output decoder. What is the output decoder? Well, it turns out we do the same thing. We use a K-map. This only has the 1 bit because it's either true or false. And we say, well, it's going to do the same thing, 0, 0, 0, 0, 1, 0, don't care, don't care. It's the same input, CS0, CS1. Make the same circle. Because there's a don't care, we're going to use it. And now we're going to say that Z is equal to not I and what doesn't change over here, it's CS1. Yeah.
You doing the output detector? Like what block are you?
This is the output decoder now. That's the column. This is when should Z be true? Z is true here, but we don't care if it's true here. And so you've just taken this map basically and turned it on the side and flipped those two columns. And this is done, right? This is just D flip-flops that have enough D flip-flops to store the next state and put it on the current state. That's all state machines are. That's all of them. It's just the next state decoder and the output decoder get more and more complicated, the more sophisticated the design needs to be, right? Because if I have 40 different options, then I need enough bits to store 40 different options, and now K-maps don't really work. So the next thing is going to be, we want to understand how these state machines are designed. But next week, after the exam, the following day, so next Thursday, it will be, we'll talk about how do we build these in Vhdl, right? Because we don't want to go, and you could build this on a breadboard. We could do that. We could take some flip-flops, a couple of and inverters, and we built a sequence detector. But it turns out to build something sophisticated like the calculator that we're planning on designing, it would be nearly impossible to do that design on a breadboard, so we're going to do it in Vhdl. We need to understand what's happening so that we can design it good. So that's where we're at. Let's design a very similar detector. But let's move on to the Moore state machine. This is Neely. This is a fair approximation of what the homework will be, Neely or Moore, and it's also a fair representation of, there will be a question on the exam. It may ask you to design the next state decoders given some detector, or I'll give you a picture and tell you to like give you a sequence, draw me the diagram, or I'll give you a diagram and I'll tell you to turn it into a table, or I'll give you a table and tell you to turn it into logic. Generally, I don't tell you to do the full steps because it makes grading really miserable. So I used to, in the beginning, I would tell you, design a circuit that detects 0, 1, 0. Now that's perfectly fine. It's a fair question because you would just go ahead and draw the diagram, turn it into a table, use the table to build the circuit, draw the circuit, you're done. It's just grading that's annoying, so you can trust that I will, well, you can be optimistic that I will probably decouple those and they'll be separate questions, but that's the kind of questions that I will ask about this. And as I said, there will be a homework, so you get a chance to practice this, and I will be posting the answers as quickly as I can write them, pretty much. So I did look a couple days ago, and a lot of you haven't finished the homework. You're a little bit behind, so make sure you catch up on the homework, because with the exam coming, you'll want to have it done. And once I start posting the answers to the homework, you start getting late marks for trying to get in late. Until I post the answers, I don't really care. But get those turned in, especially if you've already done them. You just haven't hit the submit button. Okay. All right. Let's build a Moore state machine. Now this is it. His name is Moore, but Moore state machines take more states to design, generally. I've seen, like, I don't know how many there are, but I've seen one exception where it took the same amount. But the general idea is that a Neely state machine, the output decoder, cares about two things, which is what is our state and what is our input. A Moore state machine makes that optional. It does not care what our current inputs are. It only cares about what our current state is. So this diagram is the generalized version of a state machine, which is the dashed line is only there in a Neely, isn't there in a Moore. That's why it's dashed. It's a conditional. It changes the type of the state machine. It's easy to design one or the other. It turns out most of the time, I tend to design Moore state machines because it turns out they're a little bit easier for me. And also they're a little more predictable in their output behavior for beginners. So the way the Moore state machine starts out the same, and let's just flip it around just for fun. Now we want to detect, let's do a bigger one. Let's detect the sequence 1101. Let's detect that. Okay, so we're going to have the same concept. We're going to call this I, and our output will be Z, just the same. And I'm going to change a little bit about how we draw it, because there's multiple perfectly valid ways, which we're going to come in here on reset, right? I'm going to start out and I'm going to call it S0 as well. But Moore state machines behave a little bit differently in that the output is determined only by the current state. So we put the output inside of the state bubble. So here I could do this a couple different ways. I can say Z equals 0. I can explicitly call out what is my state. Z is 0. My variable, sorry, my output variable is 0. And if I see a 1, I go to state 1. And now here, what I like to point out is anytime if I'm you and you're on an exam and you need to draw a state diagram that is a sequence detector, you should draw the correct detection path first and then go back and fill in the alternates. It's just the easiest way to do it. You're unlikely to make a mistake that way. So I'm saying 1, 1, 0, 1, so 1, 1, 0, 1. So if you recall, in the case of the Neely state machine, there were 3 numbers to detect and there were 3 states. In a Moore state machine, there are 4 numbers to detect, 5 states. It takes 1 more state to do the detection, because one of these states, its whole job is detect. So here, I could keep going Z equals 0, but I want to represent a few ways to do it. If there's only one output, I can literally just write 0. Or I can write not Z, write my variable as Z, I put the not, it says it's not asserted. Those all three are saying the same thing. State 3, you still don't have Z. State 4, now I have Z. Right, and in a more state machine, that's obvious because it's 1, 1, 0, 1, assert the detect. And keep in mind, it's each time there's a rising edge of a clock, it's evaluating the input. Okay, now I go back and I fill in the opposite of what happens, which is if I'm 0, I say put. This one is a 1. If I see a 0, so I go 1, 0. Well, 1, 0 isn't part of it, so 0 goes back. This one, I have the 0 output. If I get a 1, then that means I've seen a 1, 1. Now, this is the trickiest part of these sequence detectors, because let's consider what happens if I have a 1, 1, 1, 0, 1. Okay, my sequence is here, but there was an extra 1 on the front. That's what this is saying. So 1, 1, 1. There are 3 1s in a row. But what this state 2 is really saying is I've recently seen 2 1s in a row. So stay put. So the way that you check this is after you've drawn the diagram, you're going to feed it a couple of patterns and you're just going to follow what happens. So you're going to go 1, 1, 1, 1, 1, 1, 0, 1, detect. Yeah, that's correct. It still can detect. If I accidentally put it back here, right? If I make that mistake, because you might think, oh, I saw 1, this is the state that tells me I saw 1, 1. Well, then what's going to happen if I get that sequence is 1, 1, 1, 0. 1. That's not the detect. Even though I see the pattern, it didn't detect. That means I built it wrong. So we can do some quick sanity checks as we build these diagrams. That's why these diagrams are helpful, is because they show the flow. As you guys putter around next semester, you will see these types of diagrams everywhere as my 3610 students doodle them on everything as they puzzle through how to solve their digital systems assignments. So these don't go away. Like, this is still used at like professional design level to help you think through these control systems. Okay, next bubble, this is the 1 taken care of. So this is 1, 1, 0, 0. Well, if I see 2 zeros, that's a start over. Now this one's the tricky one, the next tricky bit. So if I see a 1, 1, 0, 1, that means I'm in state 4 with the detection. So if I see a 0, well, that's a 1, 1, and a 0, which is not part at all of my detection. So it's going to go all the way back to the beginning, right? The 0 part is, and I'm just going to join it up here because it's going the same direction. Now the 1 part, if I do 1, 1, 0, 1, 1, right? That's this 1. So I've seen the detection. Now I'm in state 4 and I see a 1. Well, this state is, the 0 doesn't matter, right? But I have 2 1s in a row. So state 2 is my, I've seen 2 1s. Now we could run a test if I wanted to do, 0, 0, 1, 1, 0, 1, 1, 0, 1. So I should hopefully have a detection here and a detection resulting from that one. So now I go, well, 0, 0, 1, 1, 0, 1, 1, 0, 1. That is 2 detections. Yes.
So when you hit state 4 on the rising edge of the clock, your Z will turn to 1,
As soon as I enter state 4, my Z turns to 1.
and then as soon as the next rising edge, it's gonna go back to 0 because you kicked back to
Correct. Yeah. So your timing diagram, if this is your state, and it goes, let me skip every other one just to make it obvious. I go, I'm just gonna write number 0, 1, 2, 3, 4, and I say 1, so I'm going back to 2. What's going to happen is Z is going to be 0, 0, it's state 4 that asserts. So as soon as I enter state 4, it goes high. As soon as I leave state 4, it goes low. So the output only depends on what state am I in. And we'll see how this translates to VHDL. And it turns out that the VHDL is going to make all of your other design simpler. State machines are such a powerful tool once we understand this and how we turn them into VHDL, it simplifies everything else. Because like we've talked about building counters, which you have to build a counter for project 2, it turns out that state machines make a really good counter. They make really good everything. Like I design so much in state machines, but the thing that it excels at, the thing where you can't avoid it, is anywhere where we start thinking, we start controlling something. But before I get to that part, let's find the eraser that I missed.
So all of the more state machine complicated when you added another state, and then that can state control state.
Yes. Yeah. And so the nice part is the state 4 is the only thing that I care about for the output decoder. So suddenly the output decoder is really simple because it's just looking for that state.
And all you had to do this was just add another state.
Yeah. But the trade-off is about to become apparent. Which sometimes the trade-off is not so steep as what we're about to see. But this is kind of the worst case trade-off. So I have the same next state table. So I still care about where is my current state, what is my next state, and what is Z. But the Z is easy because it no longer depends on I. So this is I equals 0, I equals 1. Remember how Z with the Neely state machine used to have that condition as well? Now it doesn't. The output decoder is now simple. However, by adding that state, well, if I tried to go 0, 0, 0, 1, 1, 0, 1, 1, what's state 4? Okay, well, I have to now go.
You have to add a whole other bit.
Okay. There's a whole bunch of don't cares at the end of this, which is nice. But I still have to do a 4 variable input, right? It's still going to be a more complicated design as a result. Now, there's something that I do need to say, which is that there is a technically correct way to assign states. Because there's a list of rules that you can go find in your book that says that if you follow these rules, you'll end up with the most simple logic. Because you may end up in situations that, depending on the order that you assign your state codes, the logic gets more or less complicated, basically. However, I don't expect you to know those rules. That's one of the things that I've just kind of pulled out of this course that I used to teach, because you're never going to build this on a breadboard. I would be absolutely astonished if any one of you ever did this even as a hobby. You will never do this like as a job. So I don't care if you know how to assign the state codes, because the VHDL will do it for you. It will make those assignments. But I want you to understand that there is a correct way to make these assignments. Now, to make things more complicated, remember forever ago how I talked about one hot encoding? If you look at your FPGAs, the way these state machines get implemented, more often than not is one hot encoding, which means it actually does use 1 bit for every single state. It turns out that that has some really strong benefits, because if you think about what's happening here and you look at this output, it feeds back around, and we know, right now I'm treating this as ideal, but we know that it takes some time between the clock and the output change. And we also know there's some time in between this output change and the next state updating. So there's a speed limit on this. And there's a thing called glitches that can happen, which is if we go too fast, when the rising edge hits, this isn't done settling. And now we go into some weird state and we may not know what it is. And it may even be one of those don't cares. So we have no idea what it is. So the one hot encoding basically eliminates that risk. And well, I shouldn't say eliminate, it reduces that risk and allows us to design separately. But again, you don't have to worry about that because the VHDL is going to handle that for you. So just keep that in mind, that there is a right way to assign these. And if you pick it differently, that's okay. I will suffer through the grading, right? Because it does add work if you guys don't do. I may specify just assign them sequentially so that you all do it the same, so the grading is easier. In fact, it's fine. But you might consider basically, where do these fall on the K-map? Where are the ones and where are the don't cares going to fall? That's really what matters as far as the state code assignments. All right. Back up the tangent. But now it's just fill in the table. If I'm in state 0 and I see a 0, I stay in 0. If I see a 1, I go to state 1. So notice this time I'm not even writing the state number. There's trade-offs here. One is less writing, but the trade-off being that it's less easy to read to go back and check your work. If I'm in state 1 and I see a 0, I go back to state 0. If I'm in state 1 and I see a 1, I go to state 2. State 2 is 1 is stay put. And a 0 is go forward to state 3. State 3 is 0s is go back to the start. And 1 is go to state 4. State 4 is if a 0, go all the way back. And if 1, go back to state 2, which is 0, 1, 0. The output decoder is super easy, right? It's no, 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 yes. There is a bunch more to this table, but it is all don't cares. It turns out when I actually design state machines, a lot of times what I'll actually do is here is if I'll specify rather than don't care, I'll just fill it all in with state 0, and I'll just tell it to go back to state 0, go back to the beginning. If something weird happens, just go back to the beginning. In fact, a real good way to do it is actually create an extra state that's like your error state. So it'll jump it if here, it'll go into state 5, which is error, and then back to state 0. So it'll send and let you know that something went wrong. Like that's more of a complete design. But for simplicity, which is all I'm going to ask you on this exam, right, in this class really, is we don't care. And so now we need 3 K-maps, because now it's NS0, NS1, NS2. There are 3 next state bits. So that means this is no longer 2 bits, it's 3 bits, which makes this 3 bits, which means I have 3D flip-flops in my current state. This register, 3-bit feedback around. NSD has 3 current state bits and 1 input. I will not give you more than 4 bits as an input. if I had taught you 5 and 6 variable K-maps, then we could do up to 6 variables, which, for example, just so you know, we could have like a 2-bit input and a 4-bit current state. Right, that's 6 variables. I didn't teach you 6 variable K-maps, so I don't have to do it, but like I did when I was taking this class. So don't worry about that. But let's go ahead and do a K-map, right? Where we're going to assign and this is one that generally we want to spend just a moment to think about how we want to assign this map. So last time it was I CS0, CS1. And what I want to make sure I do is that I want to either do top to bottom or across just to fill in, make my, like make the speed make sense, right? Make the order make sense so that I can go quickly. And so 0, 1, 1, 1, 1, 0. Remember, flip the columns, flip the rows. And now if I say, well, in one case, my CS0 is going to change frequently. So I'm going to keep CS0 here and CS1 there. So this is now that, and now that makes I's change more often and CS2. Let's try that one, and we can just do a quick test to make sure if this makes sense. So we're going to start here. Always, right? This is, again, I have to label, this is NS0 that we're doing, and it starts with a 0. And now if my state is 0, 0, 1, which is this state, and my input is 0, so 0, 0, 1 is my state, and my input is 0, then that goes here. So 0, 0, 1, my input is 0. So then this is 0, 0, 0, and the only thing that changes I is 1. So that's this one is that one, right? It's all zeros, so my state is 0, 0, 0. Input is 1, that guy. Now let's just check the next one. If my state is 0, 0, 0, and my down here, do I care? Well, this is 1, 1. This whole thing is don't cares, right? I think. Maybe not. Let me give it a check.
Because you have a.
Nope. Yeah, so 1, which is the one that just don't care. Anywhere CS2 is 1, and either the other 2 is 1. So here and there we go. Okay, so this is now 0, 0, 1, right? And our input 0, 1 is input is 0. That's this 0. If we're 0, 0, 1 and our input is 1, that's this one. That's that 0. We're going to skip over. We're now 0, 1, 0. That's this one. That's that one. 1, 0. Now we're here. State 3, which is 0, 1, 1. So we're 0, 1, 1, and our input is 0, 0. Lastly, we're 1, 0, 0. That's this guy. And we're going to end up with zeros in either case.
So that's just giving you the last bit of that.
The least significant bit of my next state when I finish this K-map. Now, there is a disadvantage here, right? What we've seen now is this does not simplify at all, right? It's the circle of 1 here. Oh, there is 1 that I can loop that way. This is probably the worst case for my state code assignments. And part of that is if I were to change the order of these, I could get the don't cares next to these ones by choosing better state assignments, basically. Anyways, this is a perfectly valid answer. You would just say this one, well, he's all on his own, and this one can loop that way. You would write the equation for next NS0, and you would go ahead and solve. Turns out when I did this one, I didn't really like this order, which was right. That was kind of a weird order to do them in. For the next one, let's do. Yeah, we got time. Let's just keep going, right? Doesn't hurt to do more examples. So two ways that you can do this is, now that we know the order, this is pretty easy. We could do this really fast. After suffering through that, we could just know that it's going to be 0, 0, 0, 0, right? We're just going to do that same pattern. Or we could try and spend a moment here to think about what a better way is, so that when you get to the exam, we can just follow a formula, more or less, in case you have a 4-variable K-map, and make things better. So this is always just going to be, let me do this in orange actually, just so we have a different contrast. That's going to be this 0. And if I want this 0 to be next, and I want it to go here, that means that I is my 1. So that is I, right? Because now I'm all zeros except for I, so that's that 0. But now I want this one to be next. So that the I is 0, and what is the only other one? That's CS0. Right? And so that makes that this 0. And now the I changes to 1, that's this 1. Okay, now we're at CS is 0, I is 0, and I want to go this square. That makes the only one, I want this one, so that makes this CS1 and this CS2. This one's a little bit better, right? Just because now I just go, well, now this column is 1, 1, 0, 0. Right, 1, 1, 0, 0. The next column is 0, 1. Don't care. Oh, wait. I flipped that, didn't I? I got to. There we go. And now we just start circling. And this one's a little bit more complicated, right? So I've got like a 4 here for that one. I got 4 for those ones. I don't really see a better way to handle that. So yeah. That's your K-map. In general, if you were trying to do it, one of the generally reliable ways to make your K-maps overall simpler is if your states that connect are logically adjacent. That's like the main rule, just so you're aware. So like 0 and 1 are connected, they are logically adjacent, but state 4 and 0 are also connected. So we would like state 4 to be connected to, or logically adjacent to state 0. Then that would be a good thing to do. We don't have to worry about it, but just so you know, that's kind of one of the main rules. You can go look up what the rules are in the book if you want to worry about the complexities of state assignment. So I'm going to start erasing. So as I mentioned at the beginning of this, there's really two parts to your design anytime you're building some big digital system, which is one of those is going to be your data path. That's what we're designing now. That's our ALU and the memory interface and all that thing. It's where does the data that you're manipulating travel through? The other thing that we need is a controller. That's going to be a state machine, basically every time. So, for example, remember how we have this component, the memory component, where we called this signal write, or in the entity that I gave you, it's like memwrite. And that's just saying that we're going to send a value over to memory. We want to write whatever's on this signal to that signal. That's all it's saying. Well, the controller is going to have some output signal called write that's going to go into the data paths write. Okay, that's what these control signals are about. So there's a couple different types of signals that we're going to have inside of our system. Some of them are the data signals, right? That's going to be like our 8-bit buses that is carrying the results of our sum. And then some of them are going to be control signals like write and my opcode. And that's going to be in some sort of control system that's going to start in, let's just call it idle. And it's going to sit and wait until there's some user input. And if that user input is load, then it needs to load a value, right? So I'm going to push the switches on my FPGA and push the enter button. The enter button is going to send a load command. It's going to go to a state that I might call load state. I'm just going to give it a name. The Vhdl will give it the number for me. And then the load state is going to do something like, well, in the case of the load, my outputs are going to be, well, write is 0, right? Because I'm not writing to memory. Read, which is the memory signal, is 0, because I'm not pulling anything out of memory. My op, which is this output signal, then is going to be load off, which is that constant that we've created. And it's going to send it over so that our data path, which is what you're designing now, goes, oh, I'm supposed to load something in. And it will take the user input that's there and it will put it into the accumulator, and now you've loaded something in. And then when it's done, it's probably going to go back to this idle state and wait for your next entry. And if you send the add command, then it's going to bounce out. So this is what happens if we send add. Now we're in our add state. And it's going to send out the opcode is this and so on and so forth. And then we'll have a save state, right? This is going to have a million different branches that go out of it that is all going to leave when we hit the enter button. That's it. That's how we design these big, complicated digital systems, from vending machines to the crosswalk to a calculator, a microprocessor. All of it's the same idea of let's wait for a command and then go execute the command, then go look for the next command. That's state machines. So why I like this lecture is now with that conclusion, well, especially once we get to the VHDL, you have virtually all of the tools that you will need to build any digital system other than ones that require math that you don't know yet that you'll be taught over the course of it. Because it turns out that a lot of what you'll end up doing if you go this digital design route is like communications is a really popular field around here, right? We have L3 communications, Northrop Grumman does communications. We have a lot of communications related companies here. And so turns out communications require a lot of math, but they get implemented on FPGAs using VHDL. So when you learn VHDL, then you go learn about communications, you stick them together and you have a job. Before I dismiss, we're about out of time. How many of you are done with project 1? How many of you are done with project 2? Okay, good news for everyone. We'll keep working on the projects in lab this week. The downside is I have to cancel a lab. The upside, the other downside is I'm just gonna make it an assignment. The lab that I'm canceling is a sequence. I normally have you build a sequence detector and then put it onto an FPGA. But I'll just have you design a sequence detector in VHDL and then we won't put it on FPGA. So it'll just be an assignment instead of a lab. We have a couple of interesting state machine type labs coming up anyways, 1 or 2, depending on time. Anyways, an exam week from today, we'll be reviewing the exam next time. And topics wise, we don't have a lot left. Now we're just going to start refining most of what we've learned once we get past the VHDL for state machines. So we're about there, guys.
So glad.